In this lecture, we are going to discuss the mean squared error in depth. The goal of this lecture is to ensure that you understand the mean squared error from a probabilistic perspective. This helps to give some theoretical backing for the mean squared error, and it will help prepare us to discuss the cross-entropy loss as well. As a side note, I just want to remind you that there are multiple names that we use interchangeably. So if you hear error or loss or cost or objective, these are all generally referring to the same thing. So we might say cross-entropy error, but we also might say cross-entropy loss. They mean exactly the same thing. First, let's just make sure the mean squared error makes sense in the first place. Why is it squared? Well, the idea is that we would like the error to always be positive. Imagine this scenario. One of your predictions has error +2. The other prediction you've made has error -2. If you add these two errors together, you would get +2 -2, which is just 0. Of course, this is not zero error because both of your predictions are off by 2. They should not cancel each other out. So squaring the error is a nice way to make it positive. But this still doesn't really explain why we want the square. Why not the absolute value? Why not some other method of making the difference positive? In fact, it's perfectly okay to use the mean absolute error. We just don't normally refer to that as linear regression. So when we say linear regression, usually we are talking about a linear model using the mean squared error. Okay, so let's dig a little deeper on why we would want to square the error. To understand this discussion, you have to be familiar with maximum likelihood estimation, what you would normally learn in an introductory probability course. Let's say, for example, we would like to measure the heights of all the students in our class, and we decide to model this as a Gaussian distribution. As you recall, the Gaussian distribution is the typical bell curve. It has the probability density function that you see here, which will become important momentarily. We know intuitively that the best way to estimate mu, let's call that mu hat, is the sample mean of all the heights we have measured. The question is, why is this so? Here's how we solve this problem. There is actually a method to find this mu hat. This method is called maximum likelihood estimation, as I mentioned earlier. So what are the steps? First, we create the likelihood function. Let's call that L. Unfortunately, we use the letter L for a lot of things in deep learning, so please don't confuse this L with anything else we've discussed. The likelihood is the multiplication of the probability density function at each of the x values we've collected. We consider this to be a function of mu. So here, mu is the variable, and the x's are constants because they are just numbers. They are the heights of the students that we have measured in our class. The next thing we would like to do is maximize L with respect to mu. Let's think about why we would want to do this. Just for intuition, imagine that you measure someone's height, x. Now imagine mu is very far away from x. In this case, the probability of x is very tiny. We might think that x is not from this probability distribution because p of x yields a very small value. But what if mu is equal to x? In this case, p of x yields a very large value. Thus, we want p of x to be big if it is to be representative of the data we've collected. So it's the same idea for L. We want L to be big so that mu is close to all of the data points x that we have collected. So how do we maximize L with respect to mu? Luckily, we can just ask our old friend calculus. Normally, the process would be take the derivative of L with respect to mu, and then set this derivative to 0 and solve for mu. But for probabilities, taking the log of L first usually leads to a more easily solvable derivative. The reason why this is allowed is because the log is a monotonically increasing function. Maximizing L is the same as maximizing the log of L. The value of mu that maximizes L is the same as the value of mu that maximizes log L. You can prove this to yourself intuitively by taking any two numbers, a and b. If A is bigger than B, it is also the case that log A is bigger than log B. Okay, so I'm not going to bore you with the calculation, but as always, you are welcome to do it yourself on paper using your trusty calculus skills. You should end up with the derivative we see here. So if you want, please pause the video and make sure you can take this derivative yourself. Okay, so what do we get if we set this to 0 and solve for mu? Well, you can see that we get back our original answer, that mu is the sample mean of x. This is called the maximum likelihood estimate of mu, because in order to find it, we maximize the likelihood. Here's what's important to notice about the log likelihood. If you notice, the log likelihood has the same form as this expression, where I've replaced the constant terms with C1 and C2. You'll realize that it actually doesn't matter what values C1 and C2 have, they don't affect the answer we get eventually, that mu is the sample mean of x. Although we do recognize that C2 is positive. C1 is also positive given our old expression, but it actually doesn't matter what it is at all. In other words, they are just superfluous constants. So what happens if we set these constants to convenient values, such as 0 and 1 over n? Well, we get an even more interesting expression. Little l, the thing we want to maximize, is the negative sum of xi minus mu squared. One thing you may recall from your study of calculus is that maximizing something is the same as minimizing the negative of that thing. In other words, if I want to maximize negative x squared, I should get the same answer as minimizing x squared. The value x equals 0 is the answer in both cases. Hopefully you can see right away that this is obvious. At this point, you probably get the gist of what I'm trying to say. Maximizing the likelihood is the same as minimizing the mean squared error, where the error is the difference between xi and mu. So how can we relate this back to problems such as linear regression? Take a look at these two error functions. The first error function comes from our earlier problem, finding the best mu to model the heights of the students in our class as a Gaussian. The second error comes from linear regression, make the y-hats close to the y's. How can we relate the second problem to the first problem? Well, if we say that the yi's are samples drawn from a Gaussian distribution, where the mean is y hat I, then minimizing this mean squared error is the same as minimizing the negative log likelihood. And that, of course, is the same as maximizing the log likelihood, which is the same as maximizing the likelihood. Finally, one thing we can do is, instead of saying that the mean of the distribution is y hat, we can simply say that y minus y hat is a Gaussian centered at 0. Equivalently, this is saying that when we use the squared error, we are making the assumption that the error of our model with respect to the data is Gaussian distributed with mean 0. This formulation helps us to put a probabilistic backing on the error function, and it will also help us make sense of the cross-entropy loss for classification. In this lecture, we are going to discuss the binary cross-entropy loss, which is the correct loss function to use when we are doing binary classification. Let's recap the actual loss function, and then we will use the rest of this lecture to determine how to arrive at this loss function. Since we know that this is going to be based in probability, let's think about the associated probability problem. We know that the outcomes, the y's, must be binary. That means the targets in a binary classification problem must be 0 or 1, spam or not spam, fraud or not fraud, etc. The next question is, what distribution is used for binary events? The answer is the Bernoulli distribution. Probably the most typical example of the Bernoulli distribution is the coin toss. So imagine if you tossed a coin a bunch of times and you want to calculate the probability of heads. Call that mu. Intuitively, we know that mu is the number of heads divided by the total number of coin tosses. Again, we are going to go through the process of maximum likelihood estimation to see how we can arrive at this answer. Alright, so let's say we've tossed our coin a bunch of times. Let's call the results x1, x2, all the way up to xn. In this case, the x's can only take on two values, 0 or 1. Let's say 1 means heads and 0 means tails. In order to calculate the likelihood, we need the Bernoulli PMF, which is the equation you see here. Now there's one small difference between this example and the previous example on the squared error. The difference is that, for the previous example, we were working with heights, which are continuous valued. Now we are working with coin tosses, which are discrete. A coin toss can only give you 0 or 1. It can't give you, say, 0.5 or 0.9. So we know from our study of probability that for continuous distributions, we use the probability density function, but for discrete distributions, we use the probability mass function, or PMF. So this is a PMF, and it returns a probability rather than a probability density. Since you already know the steps, let's get right to it. We create our likelihood function, which is the product of the PMFs for each of the x's we've collected. We know that we want to maximize the likelihood, but the step we have to do before taking the derivative is that we want to find the log likelihood. At this point, this equation should already look very familiar. It's in the exact same form as the binary cross entropy, except negated. As usual, if you were to take the derivative of the log likelihood, set it to 0, and solve for mu, this is what you would get. Curiously, we arrive at the same answer as the Gaussian case, the sample mean of x. How can this be? Why isn't it number of heads divided by n? In actuality, it is. Remember that x can only take on the values 1 and 0. So when x is 0, that's tails, so they don't contribute anything to the sum of x. The sum of x, then, is just the sum of a bunch of 1s, which is the number of times we flipped heads. So in fact, this is exactly the same as number of heads divided by n. As before, if we take the negative log likelihood and we put it side by side with the binary cross entropy, we can see the similarities. We can conclude that what the binary cross entropy is really saying is that yi is the result of a coin toss, where the probability of heads for that coin toss is given by y hat I. Analogously, xi is the result of a coin toss, where mu is the probability of heads for that coin toss. As a side note, you'll want to keep in mind that we also usually divide the sum of the errors by n, so that we get the average binary cross entropy per data point. This makes it just like the mean squared error in that the value is invariant to the number of samples we have. You can imagine that if we have lots of samples and we only use the sum, the error would be very large, only due to the fact that we have a large number of samples. In order to make the value of the error more meaningful, we can take the average, and that makes our error more interpretable. So to conclude, what have we done in this lecture? We have shown that, just like the mean squared error, the binary cross entropy loss function is based in probability. What it says is that, for the regression case, where we use the mean squared error, it arises from the Gaussian distribution. For the binary classification case, where we use the binary cross entropy, it arises from the Bernoulli distribution. Importantly, the common pattern between the two is that, in both cases, the error function is really just the negative log likelihood, and therefore, the solution we end up finding in the end is called the maximum likelihood solution. In this lecture, we are going to derive the categorical cross-entropy loss function, which is what we use when we are doing multi-class classification. At this point, you probably already know that the categorical cross-entropy is the negative log likelihood for some distribution. So let's jump right in and try to figure out what this distribution is. In the case where we only have binary outcomes, the correct discrete distribution is the Bernoulli distribution. So what is the correct distribution for multiple categorical outcomes? Well, unlike the Gaussian and Bernoulli distributions, this distribution is not named after a person. It is simply called, quite appropriately, the categorical distribution. The usual analogy for the categorical distribution is a die roll. So when you roll a die, there are 6 possible outcomes typically. 1, 2, 3, all the way up to 6. Of course, there are different kinds of dice where you may have even more possible outcomes. In general, we will refer to the number of possible outcomes as k. So what does the categorical distribution look like? Well, it looks a little strange. As you can see, it is a product. Each of the mu k's is a parameter, telling us the probability that the result of the die roll was k. In other words, mu k is equal to the probability that x is equal to k. So what does this mean about the 1 function in the exponent? This is what is called an indicator function. It returns 1 when its argument is true and 0 otherwise. Knowing this, it's easy to confirm that if we plug in x equals 1, we should get that the probability that x is equal to 1 equals mu 1, the probability that x is equal to 2 is mu 2, and so forth. In other words, we can confirm that this is indeed the PMF for the categorical distribution. As usual, we are going to pretend we've collected n data points, and we are going to do maximum likelihood estimation to find all the mu's. What is interesting about this likelihood is that, because the likelihood is the product of PMFs, and the PMF already has a product, we end up with 2 products in the likelihood. Also notice that there are 2 indices in the exponent here. There's the index I, and also the index k. So that should remind you of a matrix, because a matrix also has 2 indices, the row and the column. After taking the log, we know that we get the log likelihood, and we already know that the negative log likelihood is our categorical cross-entropy. So if we take the negative of this expression, we will get back something that looks exactly like the categorical cross-entropy. And thus, we can relate this back to our categorical cross-entropy loss function. Notice here that it's a tiny bit different from our log likelihood, in that we don't have an indicator function anymore. This is because an equivalent way of writing this is double indexing yik. Yik is called a one-hot encoded value because it can only take on the values 1 or 0, where each row can only have 1, 1. Remember that I represents the sample index and k represents the class label. The class label can only be 1 value for each sample. So for instance, if I roll a die, I can only get 1 number. It must be 6 or 5 or 4 or 3. It can't be 6 and 3 at the same time. So as another example, if I have a picture and I'm classifying what type of animal it is, it can only be 1 type of animal. If it's a picture of a cat, it cannot simultaneously be a picture of a dog. Therefore, only one of the k values can have a 1 representing the target. The rest of the values must be 0. You'll notice that one-hot encoding the targets like this can be quite inefficient. Let's do a simple example. Suppose we have 4 samples, so n is 4, in 3 classes, cat, dog, or bird. Suppose the targets are cat, dog, bird, and cat. So numerically, we can represent this with the vector 1, 2, 3, 1. But in order to one-hot encode this vector, we must turn it into a 4x3 matrix, or an n by k matrix, containing only zeros and ones. So the equivalent one-hot encoding is 1, 0, 0, 0, 1, 0, 0, 0, 1, 1, 0, 0. Now, suppose my prediction probabilities, also an n by k matrix, are as follows. So for each sample and each class, I have an associated probability. It's the probability that I think the input belongs to that class. After applying the categorical cross-entropy formula, we get this value for the cost. Now you might be thinking, that is a whole lot of multiplying by 0. We already know that anything multiplied by 0 is 0, so those values don't actually contribute anything to the cost. The only values that do matter are the ones which match the target. Remember, the original target is the vector 1, 2, 3, 1. What I would like to do, ideally, is to only take the log of these highlighted values and then add them all together. The question is, can I do that without one-hot encoding the target first? And indeed, this is possible. In NumPy, we can use the double indexing trick. NumPy arrays allow you to index using iterables, such as lists and other arrays, instead of just single integers. So if I wanted to take my predictions and index only the relevant values, here's what I would do. I would take y hat at I equals 1 and k equals 1. I would take y hat at I equals 2 and k equals 2. I would take y hat at I equals 3 and k equals 3. And I would take y hat at I equals 4 and k equals 1. Using the NumPy double indexing method, I can actually index all of these values at once. I simply pass in all the row indices and all the corresponding column indices at the same time. Importantly, note that by doing this, I never have to one-hot encode the targets. I can pass them directly into the square brackets. As an exercise, you should try this in actual NumPy code to verify that it really works. Just note that in code, we index starting at 0 instead of 1. And so this is the idea behind the sparse categorical cross-entropy. So when you are in TensorFlow 2.0, if you use the regular categorical cross-entropy, you are using the one-hot encoded target, which requires n times k multiplications and additions. If you use the sparse categorical cross-entropy, you are using the original target, which requires only n multiplications and additions. Therefore, it's usually better to use the original target and apply the sparse categorical cross-entropy loss.